All right, welcome back. We are Game 2005, that's Game Physics, in the fall 2020 semester at George Brown. And it's week 6 of our broadcast, and we're talking today about energy of a system. And this is where we are today. Okay, so I'm just going to grab some water while I start talking. Okay, so before we start into it, I want to talk about a couple things. Just a reminder that next week your assignment 2 is due. All right, so assignment 2 is due next week, not this week like we talked about because of the how things have translated. We move things up 1 week. So again, next week by the end of the week. And next week also notice that there is a midterm test that is planned. Midterm test is going to be a theoretical based test. So that's true, false, multiple choice. It will cover everything from week 1 to 6. Okay, that's what's going to happen. The test will be released on Monday or Tuesday, and you'll have until Friday to complete it. You'll have 2 attempts, and there most likely will be something around 60 questions. I have to kind of reform the test this semester because it's different. A lot of the questions that you'll get are going to be questions that are going to be physics related, obviously. So there's going to be some not just theoretical questions, but practical questions where you'll have to answer the question for marks, like as in figure out the formula. So the way to practice for this is there's a couple things to do. One is take a look at the formulas ahead on the presentation, as well as what I'm going to provide for you today is a cheat sheet that I will present or that I will post up on Blackboard. So that's something that I'm going to be doing for you guys. I just want to make sure that I have it. It looks like this. Let me show it to you. Okay, there's the cheat sheet. And the cheat sheet is a single page, right? It's kind of engineered so that you have most of the formulas that you'll need for the test that I'm going to be writing right here on one page. Okay, so there's nothing more for the most part, more than you'll need than this cheat sheet. So this will be up on Blackboard, and I'll put it up right now. Let's do that. So just before I forget. So item, and we'll say physics cheat sheet. So that you all know where it is. It's up on Blackboard on week 6. So please make sure you go to that location to find the cheat sheet. Okay. So that should cover most of it. Now again, it's going to be open book. So even though I'm giving you a cheat sheet, you're going to be doing a test that is going to be roughly 60 questions. You're going to get 60 minutes to do it. And this is where the cheat sheet comes in handy, because this way you can look at the formula instead of you searching around on the internet. You also get 2 attempts. So for those people who need additional time, you'll get 2 attempts instead of 1 attempt, which practically doubles the attempts that you have. If you need additional time, and if you have an accommodation that you require much more time, if I can get you guys to ping me on Discord. I know I already have your accommodation letters too, but I want to make sure that everyone is satisfied with the time that they have, and I can put you as part of a list of people that have those requirements. And what I mean by ping me on Discord, just remind me. It'll help so that I don't miss you. I don't want to miss you. I want to give you all the time that you need if you've got an accommodation. So again, DM me on Discord, and I'll make sure that you have additional time. Okay, because you'll need the additional time on this one, because there's going to be some equations that you're going to need to figure out on the test. Okay, and that means you're going to be requiring more time than normal. Okay, so that is what's happening next week. Again, notice that next week on October the 22nd, right, as an example, and that if you look at when that is on Thursday, there is no regular scheduled lecture planned. Why? I'm going to give you this time for you to do your test. So that means next Thursday around this time, attendance will be optional. I'll be here to provide feedback for your assignments and also to give you help on the assignment that's also due at the end of the week, as well as provide feedback for anything else you want or to help you with a question if you have something related to the test. Okay, but you'll have this time. So this 3-hour slot, all right, or 2-hour slot, you'll have this time between 11 and 1 to at least run once through your test, if not twice. Again, I'll try and make it so that the test runs only about an hour. So you'll have a couple of attempts within that time frame. Okay. So any questions around our schedule for this first half? And again, it's next week is the midterm test. Okay. I'm going to keep going, and then I'll take more questions after our presentation. So what are we talking about today? We're talking about energy of a system. Energy of a system. So really, we've been using Newton's laws right now for a couple things. We've been using the laws of motion. Last week we talked about circular motion and how that affects how we can use Newton's laws with circular motion. But sometimes we can solve when we try and solve problems with Newton's laws, they become difficult. So then we can use another concept to help us solve these problems. And by the way, if you'd like, even though I'm presenting them now, if you want to use energy of a system to help you with your assignment number 2, you're welcome to do so. Let me explain this afterwards. You'll see why this might help you. So the concept of energy is one of the most important topics in science and engineering. We have to discover or talk about what energy is, because energy means different things to different people. So really, the idea of energy is really the capacity to do work. Okay? That's what it's defined like in physics. When we think about it, it's the capacity to do work. We're not talking about an energy form, like you're now, Iceman, or you're now, you've turned into the Human Torch and you are pure energy. That's not the energy we're talking about here. We're talking about energy that can be used to do work. Energy is a state variable, and that what that means is it's used to categorize the physical state of an object, right? So energy, work, and force are all closely related, and the source of the force that performs work must possess a certain level of energy, this idea of energy. Objects can also store energy, and we're going to talk about that in terms of its potential energy. Okay? When work is performed, part or all of the stored energy of an object is converted into work. Okay? This is the idea behind it. Okay, so energy, in order for there to be energy, we need to be able to, the capacity for us to do work. This means that if there's no work done, then there's no energy expenditure. Okay, this is a kind of a similar thing when we say there's no force unless there's acceleration, right? Energy is a capacity to do work, and it's also expressed in a unit called joules, right? There's 2 types of energy we're going to be talking about today. One of them is potential energy, and the other one is kinetic energy. Potential energy is energy that is stored. Kinetic energy is the energy of motion, right? And is represented in terms of momentum, and we'll talk about that. Types of energy. There's lots of types: mechanical, chemical, thermal, nuclear, all kinds of stuff. We don't care about the other stuff, the other types of energy. The only energy we care about in physics for games is mechanical. Typically, we don't care about chemical energy or anything else unless we're doing some kind of simulation. If we're doing a simulation, then what ends up happening is, then we might want to take into account some of these other laws that are related to these energies. So mechanical energy is what we want to talk about. There are 2 major types of mechanical energy, like we talked about: potential energy, energy of position, or we can also think about this as stored energy, and kinetic energy, energy of motion, okay, or momentum. Mechanical energy, when we think about mechanical energy as a whole, we think about this relationship where we add potential energy and kinetic energy together in order for us to have what we call a mechanical energy, right? So one thing to note, there's a famous saying, is that energy can neither be created or destroyed, just transferred. And we'll talk about that when we talk about the system So we have a new analysis model. The new approach is we're changing from a particle model to a system model. So this is a different thing, okay? So systems are introduced, right, along with 3 ways to store energy in a system in this lesson, okay? So what is a system? A system is a small portion of the universe. We will ignore the details of the rest of the universe. Think about it as a container. I always like thinking about it as a container. It helps me out as an example when I think about it as a container. And why? Because when I think about the system as a container, then I think about applying energy to the container, so the whole container moves. I also think about it as a small game world when it comes to the game itself. Okay, so we're not thinking about the universe as a whole and the space-time continuum and all that kind of stuff necessarily. Okay, we're talking about a container, a small part of the universe. A critical scale is to identify the system. So that's the first step. And a valid system may be a single object or particle or game object, some kind of collection of objects or particles or game objects, all right? And it could be a region of space or a part of the addressable space in a game, okay? And it may vary with time in size and shape. So the system can change size and shape, okay? Which makes sense. So when it comes to problem solving, what we want to do is identify the system boundary, when the system starts and where the system ends. Again, when I think about boundaries, in my mind, I'm thinking container, right? So here's an example system. So a force applied to an object in empty space, right? The system is the object. Its surface is the system boundary. And the force is an influence on the system from its environment that acts across the system boundary. This is a really cool and clear kind of definition or kind of depiction of how a system is. So again, think about that. The surface of the object is its system boundary, or the surface, the edges of the borders of the world is the system boundary, right? Force is an influence. I'm influencing the system by applying force. Let's talk about work. Work is done on a system by an agent exerting a constant force, right? When I say constant force, that means there must be acceleration, right? So, and the product of the magnitude of the force, right, is what we're talking about. So the magnitude of delta R, or the displacement of the point of the application of the force, right, and cos theta, where theta is the angle between the force and the displacement vectors. In other words, the meaning is that if there's no movement, so no movement, the meaning of the term work is distinctly different in physics than in everyday meaning. So work in physics means that we must have movement. No movement, no work. And that's different than what we're thinking. It's counterintuitive into the real world knowledge, right? So think about this. If there's no displacement, and if I put 0 in here, so delta R is the displacement, therefore I have no work. Work will be 0, right? So the displacement is that of the point of application of the force. So if I apply the force to this box and I start moving it, if I displace it from this position to this position, that's how I can measure how much work is done, right? Because I take the change in location or position, right? And then I multiply that by cos theta. Again, this is across a single plane, right? And then multiply it by the force that's being done, that's being applied. And then I can get the total work in joules. Okay. Force does no work on an object if the force does not move through a displacement. So that's kind of something to know as a law, right? The work done by a force on a moving object is 0 when the force is applied perpendicular to the displacement of its point of application. In other words, if I'm applying a force in this direction, but I'm moving in this direction, the force in this direction is 0. Or the work done in this direction, in the perpendicular, is 0. We only care about the direction of the displacement. So the displacement is that of the point of application of the force. So that's when it starts off. So wherever P0 or P0 is that's the initial spot, the initial location, if you will. If the force is applied to a rigid object that can be modeled as a particle, the displacement is the same as that of a particle. For a deformable system, which we're not going to be talking about in this course, it goes out of scope. Deformable systems will be things like soft body physics and those kind of things, right? The displacement of the object is generally not in the same place as the displacement associated with the force applied, because we have that little wobbly condition potentially. It's we can deform a system, or for example, bending something. The part of a system can change shape. Once I start changing the shape of a system, now the displacement's also changed. Here's a work example. The normal force and the gravitational force do no work on an object. Why? Because they're at 90 degrees. Anything at 90 degrees to the motion of an object, right, produces zero work. Why? You take the cos theta, right, which is 90 degrees, and that's equal to 0. Anything that's 90 degrees, you take that 0, multiply it by the force that's being applied, and you get 0 work. However, in this direction, right, where you have force being applied in this direction, we care about that. We just don't care about the normal or the y force in this case. The force perpendicular, the work that's attempted to be done perpendicular to the motion. More about work. The sign of the work depends on the direction of the force relative to the displacement. Work is positive when the projection of the force onto the displacement vector's axis is in the same direction as the displacement. Work is negative when the projection is in the opposite direction. Work done by the force can be calculated, but the force is not necessarily the cause of the displacement. And we also think about this as that work is a scalar quantity, not a vector. Okay. The unit of work, again, is joules, or we can say it as newtons per meter, right? Newtons per meters, which is like saying, if you remember what newtons are, kilograms per meter squared per second squared. All right, because we have some kind of acceleration where force is equal to mass times acceleration, right? So that's how we can say that. We can say that joules are also newtons per meter. We can just say it like that, newtons per meter. So think about that. If I'm saying that joules is newtons per meter, or newtons times meters, right? If I have no meters, I have no work. No work because I have no motion. So in many ways, kinetic energy and work are kind of go hand in hand. Remember, energy that's kinetic is the energy of motion. Energy that's potential is the energy of position, right? Or stored energy. Okay? I also want you to think about this as work as energy transfer, right? So when we think about energy transfer, I'm transferring energy across the system boundary. This idea. Example, I'm pushing a crate. The system boundary is the crate, right? The crate's surface. That's what it would be, right? If I'm pushing against a crate to move it, as an example, or let's think about this as a loot box. I push the loot box across the surface, right? Then I'm applying work in the same direction that I'm pushing the crate, if it moves. If it doesn't move, even if I put a lot of energy, a lot of effort and work might be two different things. I'm going to put a lot of effort into moving everything, but if it doesn't move, there's zero work. Vincent, you had a question. You want to come on?
Hi, can I get on the mic for a bit?
Absolutely.
Isn't newtons per meter designated as newtons slash meter?
No, it's not newtons. I should say it's newton meters, not newton per meter.
Newton meters. So I just wanted clarification on that.
Yeah,
thank you.
It's newton meters. Sorry. Thank you for that. All right. Let's continue. All right. So So the scalar product of two vectors, again, how would you get that? It's the dot product. That's what it's also called. And what the dot product is a projection of A on or B onto A. We can say that A vector times dot B vector is equal to AB cos theta, right? So that means we don't care about the y-axis whatsoever. We take that B vector and we project it onto A, right? And that we get the direction where B is B cos theta. We don't care about the y-axis, right, in this case. So then when we look at how it applies to work, we can say that work then is the force times the displacement, the difference in position. That's what displacement is. So delta R, when I look at delta R, I think about the whole term as displacement. That means displacement for me, right? Cos theta, and you can say that it is equal to the force vector, right? Again, times the displacement vector. Force dot displacement. Sorry, this is what it means. Power. Power is related to work. Power is used to measure how long it takes to apply the work. So again, power would be work over time, or joules per second, or also called watts. Okay, so power is work over time. Okay. How about work done by a varying force? We've been talking about work so far with a constant force. But what about this varying force? Well, if you look at what these little time slices are, these are integrals, right? And actually, this is how we came up with integration in the first place. Someone said, and this is something that you've missed because we haven't done calculus this semester, but basically someone was trying to figure out the area under a curve. We're trying to figure this out. So what they did was they took some rectangles, and they took smaller and smaller rectangles that were close together, and you can see that here we have a bit of data loss, right? See this area right here underneath the curve? That area isn't being taken into account, but if you slice the rectangle thin enough rectangles, you get closer and closer to the area under the curve. Closer and closer, right? And of course, this can be figured out nowadays with modern integration techniques, all right? This idea of the total work done. So where you have the force on the x-axis, right, as an example, and then you have the displacement where the x initial and x final, you want to find the total force underneath the curve, right? So to use the original equation, work is equal to force times displacement times cos theta. The force must be constant. In a varying force, we can't use that equation. Okay. For all the intervals, we can say that work then is the sum of all of the intervals of the integrals. That's what we're going to say here, from x initial to x final, where the force changes, the amount of force changes according to the position of the object over time, right? And so this might look like a complex equation, but again, you can figure it out by using the integrals, the intervals of the integrals. So again, you would say x final minus x initial, but you would find the integral of x final, and you would subtract it from the integral of x initial, sum up that value, and then multiply it by force times the change in position. Okay. I'm just talking about it because you should know how that's done. And here we can say that since as the limit of the x, the delta x, the change in x from x initial to x final approaches 0, we can say that we sum up the integrals, the interval of the integral between x initial and x final, and we come up with this. And therefore, when we do a little bit of integration, we find out that work then, when applied to varying force, is the integral of the intervals between x initial and x final multiplied by the force that's applied across the x-axis dx. So you would do an integration on this. Again, I'm not going to ask you for this kind of work to be done, right? But you should know that's what's done with when you're applying a varying force. For us, most of the time, for our games, we don't usually do this unless we're doing some kind of simulation. We use constant force. Okay. How about when work is done by multiple forces? It's the same thing. We take the integral, because it's a varying force, we take the integral of the interval of the sum of all forces across the x-axis, and that's how we find the work that's done. Where the subscript x means the external agent that's applying force across the system boundary. Okay, I'm not going to continue with this. I'm going to move on. Work done by a spring. So whenever we talk about springs, and we haven't really talked about springs so far this semester very much, right? But we got to think about what a spring is. A spring has a natural state. So example, here's a spring in this picture B. This is the natural length of the spring when there's no force being applied, right? Forces can be applied so that we can compress an object. Forces can also be applied so we can extend or elongate an object. And then there's going to be a counter force, right? Or a spring force that's going to go in the opposite direction of our work, right? That's being done in order for the spring to go back to its natural state. That's how a spring works. Okay? Was there a burst onto the mic? I didn't realize there was a burst. I'm sorry, Madison. But does that make sense? So, in other words, if I compress a spring, I'm doing work because, look, I have a displacement from the natural state to a compressed state. Once I've compressed the object, now I've stored energy inside of the spring, and the spring force, or the force of the spring vector, is going to go back in the opposite direction of the work that I've done, right? I've actually, if you want to think about this, the system is the spring. The system boundary is the area that I'm touching the spring, right? Right here. And what I'm doing to the system is I'm compressing it, right? Although you might think about this as deforming it, I want you instead to think about it as I'm transferring energy across the system boundary. And the spring is the type of system that can store energy when I compress it or elongate it. Okay? And then it'll express the energy in the opposite direction of the work that's being done until it comes back to its natural state. There's also another thing about springs that we should know about. I can deform the spring enough so that the natural state of the spring is also changed. When I deform the spring, I break it in effect, right? If I was to stretch the spring beyond its tensile strength, then I can stretch it to the point where it won't go back to its natural state. I've deformed the spring at this point. So there is a new state, okay? Same thing with compression. I could compress a spring to the point where I have deformed it out of its natural state into another one. So it won't go back into this natural state anymore. It'll probably hang out on this side somewhere. It's possible. So these are kind of properties of springs in some ways. So if you think about this, again, takeaways is I can transfer work across the system boundary, and the system boundary a lot of time in this image is the block that I'm pressing onto. I press the block, I'm transferring energy, or I'm doing work on a spring by compressing it because I'm displacing it from the natural state into its compressed or elongated state, its transformed state. So spring forces, again, we talked about this, the spring force is equal to the coefficient of the spring, which is the coefficient of stiffness, how stiff a spring is. And notice it's a negative kx. Why? It's the direction that I'm going on the x-axis, but it's negative whatever that direction is, because the spring force is going to be in the opposite direction of the force that I've applied. And this is called Hooke's law. x is the position of the block with respect to the equilibrium position, or the natural state of a spring, and k is the spring constant or force constant and measures the stiffness of the spring. So again, we haven't really talked about springs in our in this semester. However, it is something that can apply to some games, and that's why I mention it here. I don't want to waste your time with things that are not going to be applied to games, but springs, you can make them very realistic, especially if you make things like springboards and other things like that that you want to use in a simulation, where you want to apply force in the opposite direction of the spring equilibrium location. All right. So again, when we think about Hooke's law again, the vector form of Hooke's law, it looks like this. The force vector, the spring's force vector, is equal to the force vector across the x-axis. That's what I is. That's the I component. Remember, x-axis is usually associated with the ith component, and the jth component is associated with y, right? K is usually associated with z, but sometimes it gets muddled. And usually we have this little hat that kind of says that this hat is the component of the force, right? So therefore we can say that the force across the x-axis, or the spring force, is equal to negative kx I component. When x is positive, the spring is stretched, okay, like this, or elongated, right? Then F is negative. So if I've gone in the positive direction from the equilibrium point, that means I displaced to the right, then my spring force is in the negative direction. When x is 0 at the equilibrium position, then so too is force. And if x is 0 and I haven't done anything, even if I've applied force and I haven't moved I haven't been able to displace my object, it could be because of the mass of the object or maybe the stiffness of the spring, my work is 0. Always think about that. When x is negative, the spring is compressed. Why? Because I go from the equilibrium point to the left of the equilibrium point. So x becomes negative, and as a result, the resultant force, spring force, is positive. It's going to strive to go in the opposite direction because of Hooke's law. So this is something, the force exerted by the spring is always directed opposite to the displacement from the equilibrium. In some ways, this is this aligns with Newton's laws, right? For every action, there is an equal and opposite reaction. Equal and opposite reaction. It kind of hooks into, sorry for the pun, it hooks into Newton's laws very nicely. If the block is released, it will oscillate back and forth between negative x and x until it finds rest at the equilibrium point at some point. And it also depends if the block is resting on a frictionless surface. If the block is on a surface that has friction, it will take longer to find its equilibrium. I'm just going to take a short pause now and make sure that for people who are watching this video online, that it's available to those people who need more support and who need real-time closed captioning. I do apologize, I haven't been able to do this earlier. It takes a bit for this to happen. So I'm just going to make a new YouTube video link on our Blackboard. Sometimes this doesn't work until I wait a little longer, and I think I figured out why. There it is. Going back to that presentation now. So work done by a spring then, if you notice, whenever we think about the work done by a spring, it's the interval, right, of the integral, right, between 0 and, if it's compressing, right, negative kx max, or the other way around, right? So depending on where you start, if I'm compressing or if I'm elongating or extending, then negative x max to x max, right, is what you'd substitute in here inside of the integral. And again, what you might want to do is, if you're formulating the integral, you might want to put, again, this is like the final position from the initial position. So initial position might be on the left, and then you want to go to the final position, which would be the equilibrium. And then what you would have here is you would take the integral of this. Again, the integral is, a lot of times we can also say that it is called the antiderivative. The antiderivative. I want to move back from acceleration, as an example, into velocity, and from velocity back into position, right? If I want to calculate the integral. And so what I'm looking for when it comes to work is acceleration, right? And again, this is the math. I don't expect you guys to know this math. I'm not expecting you also to use this math other than Hooke's law. So I won't be asking you to do this part, but this is how we get to this part. Okay, so the work done by a spring on the block is, if you figure this out, and if you simplify, so work from a spring, that's what this WS means, is equal to half kx I initial squared minus half kx final squared. So again, it's the integral or the interval. If the motion ends where it begins, then work is equal to 0 because there's no displacement. And by now you should know the difference between displacement and distance, where displacement is a change from the origin, right? And distance, it's the path. We want to measure the total path. All right. Spring with applied force. Suppose an external agent, F, applies or stretches the spring, okay? The applied force is equal and opposite to the spring force. So, what this means is my applied force, which is in this direction, is going to be equal and opposite to the spring force that ends up. So in other words, what I'm doing is, if you think about this model, I am investing energy or transferring energy into the spring system, because we're talking about energy of a system. And now that, because it's equal and opposite, the force of the spring is going to increase the more I compress the spring, right? Now this is not including the maximum compression that I can compress the spring before I deform it or break it. And the same thing goes in the opposite direction when I want to apply the force to elongate or stretch the spring. If I stretch the spring, there's going to be a limiting amount of force that I can put before I deform the spring or break it. Excuse me. Let's talk about kinetic energy for a second. So one possible result of work acting as an influence in the system is that the system changes its speed. So that's possible, a result of work. All right, so the system could possess something called kinetic energy. Kinetic energy is the energy of a particle due to its motion, and it can be described as K, which is the kinetic energy, is 1/2 mv squared. Okay. If we know this is kinetic energy, where K is the kinetic energy, m is the mass of the particle, and v is the speed of the particle, right? Can we not relate kinetic energy somehow into force? We can, and we'll see how force and kinetic energy match up in a second. So a change in kinetic energy is one possible result of doing work to transfer energy into a system. Well, this is what happens when I transfer energy into a spring. It goes from, I kind of move it, I've displaced it from the equilibrium point into a compressed or stretched state. And what I've done is, if you want to think about it in a different way, is I've transferred energy, I've stored it in a potential energy. Until the spring is released, there is no kinetic energy. As soon as I release the spring, potential energy, which we're going to talk about before, and we've said it already, potential energy is the energy of position, right? Where kinetic energy is the energy of motion, right? So if I displace a spring or compress a spring to the point where I build up kinetic energy, potential energy, once I release the spring, there's a transfer from potential energy to kinetic energy. The energy of position transfers into the energy of motion. We'll talk about this again. So here's how kinetic energy works. If we want to calculate the work done, then we can say that work external is the interval of the integral of the intervals between in the initial position and the final position, and the sum of all forces across the x-axis. I'm sorry. And then when you change force into MA, then you can simply say that work external is the integral of the interval between velocity final and velocity initial. So this is where this part is kinetic energy and this part is work, right? We know that work is equal to force across the x-axis, right? As an example. And once we've done these two things, we can relate one thing to the other. We can say that the external work is 1/2 mv squared final minus 1/2 mv squared initial. And we know that the external work can also be depicted as, or shown as, k final minus k initial, which is the change in kinetic energy. Now remember that kinetic energy, we start off with an amount of energy, and as it moves, the kinetic energy will be transferred. Think about energy transfer again. It'll be transferred into different places. The kinetic energy or energy of a system will be transferred into the ground, as an example, or it could be transferred into the friction. The friction will eat away at the energy of a kinetic system, right? So imagine if I have a system that's moving in a specific direction, but there's force, the force of friction that's counteracting against the system. We can say that the force of friction is depleting the energy, the kinetic energy that's being applied across the system boundary. Okay, again, a different way of thinking about it. So here's how we can relate work to energy. We can say that energy initial plus work is equal to energy final. That's pretty simple, right? And if we think of when we bring in, again, energy can either be potential or kinetic, so that we can say that kinetic energy, and potential energy, by the way, is a U. It has this U. Kinetic energy plus potential energy plus work, then, because energy itself can either be potential or kinetic. We've just broken E initial, which is energy initial, into kinetic energy initial plus potential energy initial, right? That's all we've done here. So we're saying if I take both kinetic energy initial plus potential energy initial and add work to it, this system, then we have some kind of kinetic energy final and potential energy final at the end. Typically the way it works is there's a shift, let's call it this way, a shift between potential energy and kinetic energy. That's where the shift occurs, okay? In other words, we might start off, most systems that we'll see might start off with a greater amount of potential energy, right? And zero amount of kinetic energy. In other words, there's no movement in the beginning a lot of times. No movement, no kinetic energy. Energy, remember, is work, right, in some ways. So, at the beginning, we have no movement. Then we apply work to the system. And what we do is we get movement from potential energy to kinetic energy, where the potential energy goes away and the kinetic energy rises. Okay? So here's an example of that. If I have an object and or let's go back to a spring. I apply work to a spring to compress it. I'm transferring energy, right? Through the act of work, I'm transferring energy into the spring system. I'm increasing the potential energy of the spring, right? My kinetic energy is still zero, right? As I compress the spring. When I let the spring go, I've already done my work, and now we're on this side. The work has been done for me to add energy into the as potential energy. I haven't added any kinetic energy. Then when I let the spring go, now it goes on this side. My kinetic energy goes to, it transfers from potential energy to kinetic energy, and my potential energy becomes 0. Why? All of the energy that I stored up is released into kinetic energy. That's what happens. So again, positive work increases the energy applied for a force in the vacuum of space, as an example. Negative work decreases the energy. Example would be energy loss due to friction, like we talked about, right? Often you have the combination of positive and negative work because we want to take the sum of all forces on a particular system. Positivity or negativity of work is determined by the angle. Recall that work is equal to the force vector times the displacement vector times cos theta, where displacement is s in this scenario. All right, so the work kinetic energy theorem. Here we go. Here's one of the theorems you're going to get today. It states that external work, right, is equal to kinetic energy final minus kinetic energy initial, which is equal to the change in kinetic energy, or delta K, right? When work is done on a system and the only change in the system is speed, the net work done on the system equals the change in the kinetic energy of the system. Okay, so work is equal to change in the kinetic energy if the only thing that's changed is the speed. Okay. The speed of the system increases if the work done on it is positive. The speed of the system decreases if the net work is negative. Right? Also valid for changes in rotational speed, that we talked about last week. Okay. The work kinetic energy theorem is not valid if other changes besides speed occur. Okay, so that's an important thing to note. Work kinetic energy theorem applies to the speed of the system, not its velocity. So we don't care about displacement in this case. We care about speed, distance, change over time. So that means path. So if I rotate around a, some kind of circle, on the circumference of a circle or something, I would have distance, not displacement, because I'm coming back to the origin point, right? But my speed, my change in speed is what I'm doing. A change in speed means some kind of acceleration or deceleration. And because there's acceleration or deceleration, it means that there's been force applied, one way or the other. If there's force applied, then we have work done. No force applied, no work done. So here's how we can also put it. We can say that the net work is equal to the net work is equal to the change in the kinetic energy, which is kinetic energy final minus kinetic energy initial. An example, what is the net work required to accelerate a 3 kilogram object from 2 meters per second to 4 meters per second? Let's start with this. How do we find that? What do we do here to find that? We want to find the net work. What do I put there? Help me out here as we do this together. This is a very simple example. So we know that K, if we look up, right? If we look at what kinetic energy is, we talked about kinetic energy, right? Kinetic energy is 1/2 mv squared. Can we not use that? Right? 1/2 mv squared. Okay. If we know that that is kinetic energy, can we substitute that in? So for example, we know that, let me just grab this 1/2 mv squared here, right? And substitute it into kinetic energy final. So what I want to do is I want to take this and just tab in there, right? So we're going to say that this is kinetic energy final, whatever that is, right? Oop. Oop. I love it. Come on. There we go. Kinetic energy final, right? Minus kinetic energy initial. So we'll do the same trick. So this is kinetic energy initial, right? Do you agree that we should do this? Will this help us do what we want to do? Because what have I been given? 3 kilograms and from 2 to 4. All right, let's do the next part. If it may make sense. From 2 . I'm just subbing in 2, 4. Okay, that is, I can just get rid of that, the subscript, but I'll keep them in for now to make it easy. We know what mass is for both sides, although it would cancel out, right? We're going to put in 3. Okay, so then we say, let's figure out the next part. Again, I'm just calculating it based on what it is here. So we're going to say 0.5 times, so first of all, do the exponent, bed mass, right? 4 times 4 is 16, right? Times 3 times 0.5. So the first term is 24, this part. Okay, and the second term is, again, we take 2 times 2 is 4, times 3 times 0.5. So the second term is 6. 4 times 3 times 0.5. Yeah, I won't be able to do it. 6. Okay, 6. 6. And 24 minus 6 is 18. 18 what? If I'm going to say it's 24 minus 6, what is 18? 18 what? Joules. 18 joules of work. That's the net work that's been done. Do you agree? Does this make sense to you? So again, I took kinetic energy. We know kinetic energy is 1/2 mv squared. Kinetic energy final, meaning the final speed, right? As an example, times the mass, right? And we did the same thing for the initial speed times the mass and velocity. And once we've got that, then we can figure out the network. It's pretty simple. Okay, let's continue. Potential energy. Okay, again, I kind of mentioned this a bunch of times now. Potential energy is energy determined by the configuration of a system in which the components of a system interact by forces. The forces are internal to the system as opposed to external, and can be associated with only specific types of forces acting between members of a system. Wow, it's a lot of words to say. Potential energy is storage. I want to store energy somewhere, somehow. I'm storing energy. That's what potential means, right? It's not energy of motion. It's energy of position, or in other situations like batteries or something like that. Think about it as a battery. I'm storing energy in a battery. I've got potential energy. When I'm using energy, I've got electrical energy, right? As an example, I'm moving from one type of system to the other. The battery doesn't have kinetic energy because there's no motion for the battery, but it has electrical energy. The electrical energy transfers from the potential energy that's stored in the battery in the system to electrical energy when I draw it out. Okay? In the same time, when we think about kinetic potential energy, we think about the block is the system and 3 external forces act on it. We've got an external force that goes in this direction, right, as an example. We have a displacement from this position to the final position. We have the normal force that's pushing up from the ground, as an example. And so we can say that this is the work kinetic energy theorem example, right? But what about gravitational potential energy? We just talked about potential energy. If I take a physics book, right, as an example, and I lift it a certain distance from the ground, right? What we say is, as I lift it up off the ground, right, I can say that the potential energy, because it's energy of a position, is mgy final minus mgy initial, right? Mg, mass times gravity. If you think about what this is, if I let an object go, m times acceleration is force. Force times a particular, on a particular axis, force across the x-axis, force across the y-axis is work, right? If you think about it. And this is the way we find the energy that's stored as potential energy. It's based on the height of an object normally for us. So the higher an object is, the more we can say that it has more potential energy that's being stored upon it. And this is based on the displacement on the y-axis, which is what we're seeing right here. The displacement vector across the y-axis, so y final minus y initial times the jth component, ij, right? We can say that the displacement is equal to the potential energy in some ways that is being stored, or directly proportional to the potential energy that's being stored in the system. So in other words, if I raise an object off the ground, if that object has the potential to fall, I'm actually in effect storing potential energy inside of it. If I let the object go, the potential energy transfers into kinetic energy. Right? And that transfer happens when it reaches peak speed. So we can assume that the book in the previous example is allowed to fall. There is no change in kinetic energy since the book starts and ends at rest, right? The change in kinetic energy. But the change in potential energy changes because we have something called gravitational potential energy. All right? If the kinetic energy, if this thing was to fall forever, right, as an example, then there would be a transfer of kinetic energy. But here what we have is, we have that the external work that's being done, right, is equal to the final position on the y-axis times mg, mass times gravity, minus the initial position. Okay, this is what we saw earlier. So gravitational potential energy is what we're dealing with right here. The spring force, that's another type of potential energy. Those are the two that you're going to be asked about on the test. The majority of them, something to do with gravity, something to do with springs. I'm not going to ask you questions about batteries and electricity because this is not that kind of course. So we can say that UG, U meaning gravitational potential energy, UG, potential energy, is equal to mghy, or mgh, which is a good way of saying it as well. We can just ignore the y-axis, right? We can say that it's mass times gravity times height, the height that I've brought the object towards. Units are in joules again. It's a scalar, all right? It's not and the potential energy is not a vector, okay? And we can say that the external work is the change in potential energy, the change in potential energy. So gravitational potential energy depends only on the vertical height of the object above the Earth's surface, or in the case of another planet, the gravitational body, whatever that gravitational body is. So Ian's asking a question. If a ball is accelerating straight up while it is still moving in an upward motion, would it still have potential energy if it has not yet reached its maximum height? Actually, what's happening, Ian, is there's a transfer of energy from kinetic energy to potential energy, because what's going to happen with that ball is it's going to start to slow, because there's going to be a negative acceleration due to gravity as it goes up higher and higher and higher. When it reaches its peak, it's reached peak potential energy, because that's the highest height that it's going to be above the Earth's surface. And then what's going to happen is, as it starts to fall, the potential energy is going to start transferring into kinetic energy. Okay? Until the potential energy becomes zero when it hits the ground. And that idea is a way we can think about how things move. Instead of thinking about it just in terms of Newton's laws, we can start thinking about it in terms of energy transfer. Once I start thinking about it in terms of energy transfer, my life becomes easier in some ways. Why? Some complex problems are more difficult to figure out with Newton's laws only alone. And that's what we said at the beginning of this thing. Okay, there's two types of potential energy. We're going to talk about this: elastic potential energy and gravitational potential energy. Actually, elastic potential energy is going to come into play when we do elastic collisions. We'll talk about that later on. But let's think about this. So elastic potential energy is associated with a spring, like we talked about before, where we use Hooke's law. the force of a spring is equal to negative kx, right? So the work done then is 1/2 kx final squared minus 1/2 kx initial squared. That's the work done by the system. So therefore, when we think about this, and this is a great picture, actually I really love this one because it says the potential energy of a spring is equal to simply 1/2 kx squared. That's the elastic potential energy. Let's take a look and see how that looks. If you actually zoom in here into your presentation, you can see it too. So think about this way, right? Right now in this initial state, the block is separate from the system. Let's say the system boundary is the spring head right here, and we're at equilibrium. Right now, there's no kinetic energy, there's no potential energy, there's no total energy. However, once I start applying work, I do work on a block on the system by pressing the block with a certain mass, and I change its I displace the block from, or the spring, sorry, from its equilibrium position to a position that's been compressed. What have I done? I've taken energy, I've done work, and I've applied energy in terms of potential energy. So my total energy of a system is here right now. As I continue to apply my work, right? I apply work in a specific position. I keep on compressing it until I can't compress it anymore. Maximum compression, we'll say. Okay? When we've reached maximum compression, we have the total energy built up in the system is max at 100%, right? Notice that the potential energy meter is really much high. It's like completely high. Kinetic energy is still zero. Why? We don't have any energy of motion. So therefore, it's all into potential energy. However, as soon as I let it go and it starts displacing back towards the equilibrium point, there's a transfer of potential energy into kinetic energy. The total energy of the system remains constant. Why? I've already applied the work to the system. I've applied the work across the system boundary. I've applied energy, or given the whole system energy. Okay? And that's why the energy stays the same after it's been applied. Notice that the total energy is not total yet. It's not 100% yet until we've reached maximum compression. Okay? And then when the spring will keep oscillating back and forth, and eventually will find its equilibrium again. When it does, and the reason why the oscillation occurs and why it will stop is two reasons. One, this spring, as an example, is on the x-axis, or displayed on the x-axis, right? We might have friction across the x-axis that will deplete the energy, kinetic energy, as the spring moves back and forth, right? It will definitely deplete it because of the friction of the block. Afterwards, the other thing that's going to start slowing down the spring from oscillating is the stiffness of the spring itself, the K value, right? It's going to keep on slowing down because it's going to try and find its equilibrium. When it reaches equilibrium, the energy of the system will drop because there'll be zero kinetic energy anymore. So it'll move from, this will start to peter out, kinetic energy, and so too will the total energy of the system. And remember we said that energy cannot be created or destroyed. Where does the energy go? So if it's let, a spring will keep bouncing back and forth. And I gave it energy. So where does the energy end up going? Because we said we can't create energy and we can't destroy energy. So where does the energy go? Guys, I'm looking for some answers. If you put your hand up if you know. And then you can, maybe come on the mic and talk to me about it. This is a key kind of learning for me, for you guys. Is there any brave soul out there that wants to tell me where the energy goes? To the block? Well, the block helps deplete the energy because the block is in contact with the surface, so it could deplete some of the energy, but then you see that there's a separation between the block and the spring. So now what happens? How does the spring keep oscillating back and forth until it stops? Why would it stop? Why doesn't the spring go on forever? Think about it. Even if the spring was positioned in a different place, if the spring was vertical instead of horizontal, it would still stop at some point. Why is that? Friction, okay. There's also air friction, right? There's air friction. There's also stiffness of the spring, right? So where would the energy go? The energy would be lost in heat and noise, right? Back into the wall? Not really. It would just be, because this oscillation would go back and forth, the oscillation itself would create heat, believe it or not, because we're compressing and we're also extending the spring. Try it on yourself. Try and make a spring, move a spring back and forth fast enough. You'll create heat, right, in the spring itself, right? Why? I'm transferring energy, and it's an inefficient transfer between the spring force and the fluid forces that are inside of our air to slow it down. Here's something. What about a spring in space? Would a spring in space keep going on forever? So there's microgravity. It's no gravity at all. Would a spring stop? Would a spring stop? How much energy loss would you have in a vacuum where there's microgravity or very little gravity and there's no other friction forces whatsoever out there? Would it stop eventually? And the answer is probably would, because of the stiffness of the spring. The stiffness itself would act as an energy damp, if you will, right? And it would also create, it would try and create noise and heat, even so, because they're still moving back and forth. Anything that's moving like this, there's going to be, it would take a long time, a way longer time than being in an atmosphere, right? But if you think about it, it's energy transfer that's happening. Energy transfer, whenever there's energy transfer, there's energy loss, because there's no perfect energy transfer either. If there was, well, we'd have perpetual energy, wouldn't we? And we don't. So the elastic potential energy stored in a spring is 0, right, by default, when the spring is not deformed. When I deform the spring, whether it's extension or compression, there is a maximum, I can read a maximum compression or extension, and when that happens, the elastic potential energy is always positive. X squared will always end up being a positive amount. And it goes through each of these stages that I just talked about, right? When we compress it and it goes through each one of these things. So the energy associated with an object's temperature is called its internal energy, right? An object's temperature. In this example, the surface is the system. The friction does work and increases the internal energy. Remember, we just talked about kinetic energy. Internal energy is a different type of thing. I just want to point it out to you, but we're not going to use it. All right, because usually we deal with things like potential energy and kinetic energy in games. So forces are said to be conservative, right? So the work done by a conservative force on a particle moving between any 2 points is independent of the path taken by the particle. The work done by a conservative force on a particle moving through any closed path is 0, right? Conservative forces. A closed path is one in which the beginning and the ending points are the same, right? Examples of conservative forces are gravity and spring forces. So that means that work done by a conservative force on a particle moving through any closed path is 0, right? At the end, this conservation of energy means exactly what we just said. Energy cannot be created or destroyed, only transferred. So we can associate any potential energy for a system with any conservative force. We can say that work internal in general, so let's say internal energy, like we talked about, heat, is equal to the negative change in potential energy. Non-conservative forces, on the other hand, does not satisfy the conditions of conservative forces. Non-conservative forces acting in a system cause a change in the mechanical energy of the system. So where I add where the energy of the mechanical energy, that's what E mech is, right, is equal to kinetic energy plus potential energy. K is the kinetic energy and U is the potential energy in the system. All right, non-conservative forces. The work done against friction is greater along the brown path, right, than along the blue path, because the work done depends on the path friction is a non-conservative force. That's kind of a weird way of saying things, right? So if work done on one path was greater than another path, right? So if work done against the friction is greater along this path than along this path, work done against friction, okay? Because the work done depends on the path, I'll say it again, friction is a non-conservative force. Why? Because we want to add up, and again, we're going to use these intervals again. We're going to say the internal work done on a system, or conservative forces, is equal to the integral of the interval between the final position and the initial position times the forces across the x-axis, or when we break it down and get the interval, it's negative delta U, where U is potential energy. And we can also say that the force across the x-axis is the derivative, the negative derivative of U over x, which is exactly kind of what we're saying, delta U over delta x, which is exactly what we're saying up here. Right. All right. I'm going to move on. So the force of static friction, again, we can say that if we look, instead of looking at du over dx, which is the derivative, it equates to negative kx. This is just the proof that that we use for Hooke's law. Okay. So energy diagrams, we're going to talk about that, and equilibrium. So motion in a system can be observed in terms of a graph of its position and energy, right? In a spring mass system like this, the block oscillates between the turning points x, if the block was connected to this thing, right? X is equal to negative x max, which is the maximum compression, to positive x max, which is the greatest stretching or elongation, right? The block will always accelerate back towards x is equal to 0, where depending on which side of the equilibrium it's on. All right, so that is what I wanted to cover today. Let's talk about some examples. All right, and there's some bad ones here for you too. Some of these, by the way, that I've given you, where you can try out for yourself, is they're going to be eerily similar to the questions you're going to find on your test. And I said that a bunch of times. This means that they're almost going to be the exact same, guys. So if you take these examples and study them, or on your test, if you refer to some of these pages, they'll give you examples. If you've done the examples in lab, as an example, it'll give you an example of how to do this stuff to save you some time. Because if you try and look everything up, you're going to run out of time. Okay? So example, a force of 50 newtons acts on the block at the angles shown in the diagram. The block moves a horizontal distance of 3 meters. Okay? Horizontal distance. That's good. I got 50 newtons. That's force. I've got meters. That's displacement. How much work is done? Work is equal to 50 newtons times meters, right? Newtons times meters times cos of the angle, right? Because we've given the angle here in the diagram of 30 degrees. Okay? So we multiply them out. So force in newtons, meters, displacement in meters times cos of 30 is equal to 150 times cos of 30, which is 129.9 joules. That's the total work done on this system, however bad it looks. Pretty simple. Here's another really bad one, but also one that you might see. Example, calculate the work the bull will perform to push for 2 meters a 10 kilogram box sitting on the ground if the coefficient of friction between the box and the ground is 0.5. Assume that the box is being pulled at a constant velocity. These are all key points. Okay, we've been given a lot of information here, and let's take a look more closely at this diagram, right? Even if it's poor, right? So we have the displacement in meters being 2 meters. We have, these are the things we know, right? We have a 10 kilogram box, right? We have the box is sitting on the ground, right? And what we want to calculate is the work, right? Well, what is the angle? Because the ground, there is no, it's straight, right? We haven't been given an angle. When we start subbing things in, we know the force of friction is what we care about, because it says the force of friction, assume that the box is being pulled at a constant velocity. This is the box, let's say. And we're going to go over here, right? The work the bull will perform to push 2 meters a 10 kilogram box sitting on the ground if the coefficient of friction between the box and the ground is 0.5. Well, we know a couple things, right? We know that the force of friction times the displacement times cos theta is what we want to find, right? So the force of friction, how do we find that? mg, right, times k, or the coefficient of friction. So if we know that the mass is 10 kilograms, right, and it's 9.8 meters per second is the gravity, right? It's 98 newtons divided by 2 because of the force, the coefficient of friction, 0.5 times 98, right, is 49, approximately 49 newtons. That is the force of friction that we've been given. Multiplied by meters, so it's this times meters times 1 meaning cos of 0 because we're going on a straight line. We don't have an angle. It's equal to 98.1 joules. So pretty simple stuff again, if you think about it, this example. And there's going to be some examples for you to do. All right, here's one. Calculate the amount of work done by pulling a 1,000 kilogram brick of gold for 3 kilometers on the ground at an angle of 10 degrees if the coefficient of friction is 0.25. Assume the box is being pulled at a constant velocity. Again, really important information. So, how do we get all this? This is, by the way, from the book, right? It's by the book, right? Well, let's think about all, we can model the block as a particle for a second, okay? And again, we're looking at that same equation. Work, right, is equal to force times meters times cos theta, right? Well, the thing is, we're getting some amount of force that's happening. So the angle is 10 degrees, right? So what we're getting is the force of friction, right? And we're multiplying it by mass times gravity. So that's the first part. Force times static, kind of this part here on the top. Look how it says here. 0.25 times 1,000 kilograms times 9.8 meters per second. And then we have something else on the bottom. Why is it that we have a thing on the bottom at all? Why do we have this? Why is force pull is equal to something mg times mu, which is the coefficient of friction, over cos theta plus mu sine theta? Where do we get this from? How come? What do I have? This is the first equation that we've put down here. How come I have this? Well, let's think about what we've been given. The amount of work done by a 1,000 kilogram block. We have the 1,000 kilograms. That's m. We've been given 0.25 as the force of static friction, or the force of friction, sorry. And we've been given g, 9.8 meters per second. So we can take this top part, no problem, right? But then we said it's going to be moving over 3 kilometers. 3 kilometers. So what work across the distance? This is the displacement, 3 kilometers, 3,000 meters. So we want to do something that looks more like this. Force pull times, and we want to find the total force that's being exerted, right? So we know that force is equal to ma at some point, right? Ma. We still don't forget the forces that are being applied here, right? Because we have a force, in this case, across the y-axis and a force across the x-axis. We have to break this down into its component forces. And that's why we get sine theta and cos theta. All right, that's why we have those at all. Because we have a less amount of force, right, across the x-axis, because some of that force is being applied on the y-axis, right? So when we get force, the force of pull is the first thing we calculate, this part. And then once we know what the pulling force is, which is this, then we multiply it by the displacement, which is 3,000 meters. Again, multiplied by cos theta. So this part is the actual work formula. This part up here is the force formula, trying to figure out the force the object is generating based on mass times acceleration, right? And we're going to get a difference because of the component forces. Okay. I think this is the last one, and the last two are for you. When doing a chin-up, an athlete lifts her 55 kilogram body a distance of 0.25 meters in 2 seconds. All right? What is the power delivered by the athlete's biceps? That's interesting. Power, we know, is work over time. Work can be broken down into force of gravity, right, times displacement times cos theta. In this case, cos theta is a straight line up and down. Because the angle is 0, we're not going side to side or some weird angle. It doesn't say that in this kind of chin-up. She's not doing some kind of kipping chin-up or something crazy. Then it would be multiplied by 1. So force of gravity times displacement times 1. Cos of theta in this case would be 1. 55 kilograms, right? Multiplied by, so force is also mg, 55 kilograms times 9.8 meters per second, multiplied by 0.25, which is the displacement, over a time of 2 seconds is 67.375 watts. That's pretty good. Okay, this is a good one. And I'll leave these ones with you to do during lab, all right? A 90 kilogram bike started rest from the top of a 500 meter long hill with 30-degree incline. Assume an average friction force of 60 newtons. Find the speed of the biker at the bottom of the hill. What does this sound like, guys? This sounds like assignment 2. That's what it sounds like, if you think about it, right? Let's map it out for a second. I'm going to draw it out so you can get what I'm saying. So let's do it like this. I'm going to draw, here is the hill. Okay, so let's draw it so we can see it. Okay, so that's the hill. And it says that the top of a 500 meter long hill with a 30-degree incline. All right. I'm just going to draw it and we'll see where it goes, right? So let's say we're going to draw from here. Let's suppose that a 30-degree incline kind of looks like this. Let's just say. Maybe more. I'm just eyeballing it, okay? That's the incline. And 30 degrees is actually going to be shown here. Again, you can draw this any way you like. Remember that. So, but I'm just visualizing here for you at the beginning. So I'm just going to draw this out. So there's the ground, right, as an example. And I'm just drawing this incline for you, which is kind of like what you would see in this example thing. So now we know that this distance here is 500 meters, right? So let's put down the things that we know. Always start with those. So if I'm going to draw the diagram, this would be 500 meters, right? And again, let's rotate that diagram just so that just like we did in our sketchbook program. So this is the distance. 90 kilogram bike started at rest from the top of a 500 meter long hill with 30-degree incline. So we know this is 30 degrees. Okay, so I'm going to put 30 in there so we know what this is, right? And I think I might even have an arc that I can use. Let's see. It's arcing in the wrong direction. I wish I had better tools on this thing than what I have, but whatever. Let's just draw, and let's see if I can draw this Okay, that's a straight line. Oh, wait. Okay, I do have an arc. Sorry, let's try that again. It's this one, but I want to do this to here, and to here. Oh, there we go. So there's a 30-degree arc, right? So my 30-degree arc, 500 meters, right, as an example. And we know that the 90-kilogram bike's at the top. So let's put that loot box at the top. I said loot box because this is exactly what I've asked you to do in many ways, right? So let's say 90 kilograms. Different measurements, but it doesn't matter. Here's my 90-kilogram box, right? This is where it starts. It's going to fall down this hill as an example. And we know that the average friction force is 60 newtons. Okay, so that means that there's going to be force pushing back this way, right? Across to slow things down. That's going to be your deceleration value, if you will, right? It's pushing back this way. And the force that's pushing back that way is 60 newtons. With 60 newtons, right, we have force is equal to mass times acceleration. Okay? And friction, right, is based on the coefficient of friction times mass times gravity. We haven't been given those values. Okay? So there's a couple ways to figure out this problem. And I'm going to talk about this, and you can figure it out in lab. But let's talk about this a little bit. So 16 newtons. All right. One way to figure this out the long way would be to sit there and go, okay, so I'm going to draw a particle free body diagram, and I'm going to figure this out like this. I've got forces. It says, but what it's asking for, find the speed of the biker at the bottom of the hill. Nowhere does it say work or any of that stuff. However, here's what we know. Here's what we know. We know that 90 kilograms is where this thing is, what this thing weighs. We know that. We also know that this is 500 meters. Can we figure out, can you do this? Can you do me a favor? Help me figure out what this is. What kind of triangle is this? What kind of triangle is this? If this is 30 meters, how do I figure out the length, this side here? I want to find this side. What can I use to figure out this side? And we'll stop here for today after we do this one. We know that this is 90, right? We know that this is 60. So it's a 30, 60, 90 triangle, right? 30, 60, 90. We know that this is 60 degrees. That's fine. But what is the distance? What is this? I want to find the height of the object. What is this? Let us solve the triangle here. How do I find the height of the object? What do I use? I could use, right? Let's go to that cheat sheet that I gave you. Come on. We have a cheat sheet that's going to help you with your stuff, right? So how do I use my cheat sheet? Because it's going to come up next week, actually, right? So I'm looking at my cheat sheet. I've got displacement. I've got kinematic equations. I've got motion. You know, I've got circular motion and maximum speed. Newton's second laws here. You know, most of the things that I need, but I'm missing one equation. And then, by the way, I recommend take this cheat sheet and add to it. Add to it, right? What's missing, you know, as an example. Come on. The trig equations. Okay. I have a cheat sheet for that too. Hold on a second here. I have a cheat sheet for that too. But it's more of a calculus cheat sheet than a regular. So these are all my trig equations, right? I also have got rules for integrals and a bunch of stuff. Because remember back in the day we used to do integrations and derivatives, and we don't do that anymore. So these are all the things you would have needed for your for stuff. So this is your integration stuff. This is your sine, cosine, tangent, and all that stuff. What are we missing? What are we missing from this cheat sheet? We got power law, Root's law, we got all this kind of stuff, but we don't have what we're missing. Come on, guys. How do I get, what's the relationship, right? It's opposite, right, over adjacent, right? Opposite over adjacent, right? SOHCAHTOA or SOHCAHTOA is what I like to use, right? I always think about SOHCAHTOA. So SOHCAHTOA. SOHCAHTOA. So if I have the hypotenuse, right, and I want to find the opposite, right? So what I want to find is the sine of 30 degrees is opposite over hypotenuse. Opposite over hypotenuse, right? Whereas cosine ka is adjacent. This is the adjacent, right? Over hypotenuse. Adjacent over hypotenuse. Cosine of the angle is adjacent over hypotenuse, right? And we know the tangent of the angle is opposite over adjacent. Tan of the angle is opposite over adjacent. This might be the best, this is one way of figuring things out, right? We can find out all the angles. If we have the angle, right, then we can figure out, and if we have one of the sides, like we do, like in this case, we have the angle, which is 30 degrees, and we have the hypotenuse, we can figure out the opposite, right? So we can sub that in. So is sine, let's try this out, oops. Let's go back to that calculator. So sine of 30 degrees, let's try to figure this out. So 30, and let's see if I can go to sine. So sine of 30 is 0.5, right? And is equal to opposite over hypotenuse, right? So sine of 30 degrees, 0.5 is equal to opposite, this one, over hypotenuse. So if I multiply both sides by the hypotenuse, right, I can say that it is equal to 0.5 times 500, right? So times 500. Would that mean that my opposite is equal to 250? So if 250 is my height, and that's what I figured out, now I have something else I can use. I know that I've got potential energy here because of my height. My potential energy, or U, right? Again, this is an alternate way of doing this for you guys, right? U then, right, is equal to mass times gravity times height. Mass is 90 kilograms times gravity, which is 9.8 meters per second, times height, which is 250 meters, which we just figured out, right? So that is my total potential energy. Potential energy is in joules, right? Once I have my potential energy and I calculate this, I can transfer potential energy to kinetic energy. Kinetic energy would be down here, right? So let's try to figure this out. So if I said 90 times 9.8, right, times 250 is 220,500 joules. Right? We know that the equation that we want to with work and energy, right, is work, it's potential energy plus kinetic energy, right, plus work is equal kinetic energy final plus potential energy final, right? Well, that means that my kinetic energy final, if there was zero friction, right, By the way, we also know that this is going to transfer into kinetic energy. And we know what kinetic energy is. Kinetic energy, these are just some hints for you guys, right? To start thinking about this. We know kinetic energy is equal to 1/2 of mv squared, right? That's what it is. 1/2 of mv squared, where mass is equal to 90 kilograms, right? V, we have no idea what that V is. So we need to know that it is V squared, right? V squared, right? So if there was zero friction, so there wasn't this friction problem at all, right? Then we know that if I solve for V squared, and I know that at the bottom over here, that my total potential energy is going to transfer into kinetic energy, which means that I can say that my kinetic energy, right, 220,500 joules, right? And remember, what are joules? What are joules? Because we also have a measure of joules over here. We did a bunch of these little things here, right? Okay, so I'm just going to bring you back to some of the stuff that we talked about, right? We said that 1 joule is Newton meters, or force, right, times distance. Force over distance. That's what joules are, right? Okay. Again, hints. If this is Newton meters, right? So we can convert this to Newton meters. We can say that this is also equal to a number of newtons, right, times meters. Okay? Newtons times meters. 500. How many newtons of force? If I want to convert it. If Newton meters, right, newtons is force. Newtons, right, is made up of mass, right, and acceleration. Force is what that is. Force over distance. Force is equal to mass times acceleration. We know the mass. We don't know what the acceleration is going to be, right? That's A. So therefore, if I wanted to find out what A is, I would divide by 90 times 500. So we can say that then, if I want to find the acceleration, right? I want to find the acceleration, then I can say that this is equal to 220,500 joules divided by 90 times 500. Actually, let's do, which is what, 45,000? 90 times 500. Yeah. 4.9. That's interesting. What a relationship that is. So that works out, right? Because 4.9 is 1/2 g, 9.8. So acceleration then across this curve with what we have is 4.9. But that makes sense, right? That makes sense because, look, we calculated that this would be 0.5 because of the angle, right? So we know that acceleration, we know some things. We know acceleration is equal to 4.9, right? We know that. What's the negative acceleration that we would have here? If this acceleration was 4.9, we want to subtract the acceleration because of mu, right? Mu times mg, right? We could find this out. If we have 60 newtons and we have the kilograms, we know what mu is, right? Mu times mg. We can break this down, right? We also know that 60 newtons equals to force, is the force, which is mass times acceleration. That's the negative acceleration that we would have in the opposite direction, right? So, and it's going to be applied to the mass. It's related to mass. So 60 newtons, how much negative acceleration is that 60 newtons? right? I'm just putting it out there to see. We have a lot of information that we maybe don't know that we have. So if I take in 60 newtons of force, right, times mass times mass times acceleration, right, is equal to mass times acceleration. I want to find the acceleration. I divide this by the mass. So 60 divided by the mass. The negative acceleration is 0.6666. So that's the negative acceleration, 0.666, non-terminating repeating. Right? In the same direction as this is going. And if it's consistent, that means my acceleration from here to here is less than 4.9. That's what it would have been. 4.9 would have been there if I didn't have friction. But if I add the negative friction, then I have an acceleration. My friends, once I have acceleration, I can find the terminal speed, right? Which is not a problem. So lots and lots of stuff, right? I have lots and lots of information for you that you can use. So I recommend when you're in lab, think about using potential energy transferred to kinetic energy. How do I do that? It's moving from 220,500 joules of potential energy is going to move into some amount of kinetic energy minus my force, minus my this amount of energy, right? And if you think about this energy as well, we can think about it in different ways, not just acceleration, but we can also think about this as work being done, right? What is the acceleration? I'm moving, right? Negatively moving the block, if you think about this. And work, right, is equal to force over meters. I'm applying 60 newtons of negative force over meters, over 500 meters. That's the work, right? And that's also expressed in joules. So that's another way to think about it. Let's think about that one, all right? So if I take that, and if I say, okay, so 60 newtons, that's the force. And then again, I'm thinking, I don't care about the, this is the angle, all right, that I'm applying to. So I have to keep in mind cos theta here, right? But because we're moving over 60 over this straight line, right, and the angle of the force is perpendicular, or sorry, parallel to my motion, then it'll be cos of 0, because we're not moving, we're not trying to do it from the ground here. We're on this angle, which means our frame of reference is rotated in this case for the friction. So 60 times 500, right, which is 30,000 joules of energy, right? 60 times 500, right? If I didn't mess that up, 60 times 500. So if I know it's 30,000 joules of energy, then I can just subtract it from my potential energy. So I can take my potential energy, 220,500, minus the 60,000 joules of energy, which works out to be 160,500 joules. That's how much kinetic energy I have. 160,500 joules is what I have left over. Right? Since I know this, and I know all this, right, which kinetic energy is 1/2 of mv squared, then now I have enough for v at the bottom, right? I can sit there and say, well, that's pretty cool. Let's take 0.5 times 90, right, which is 45, and divide 160,500 divided by 45. So 160,500 divided by 45 is equal to 3,566. I want to get the square root of that, right, which is this, which works out to be 59 meters per second, my friends. That is the terminal velocity down here. 59 meters, 59.72 meters per second. Does that compute to you? At the bottom. So what did I do? I figured out when I talked it out of my head, right, that my potential energy, and I had to do a couple of steps here. I had to figure out the height of the hill, which is just using trigonometry, SOHCAHTOA, right? Once I used the height, I got the height of the hill, I was able to calculate, because we know the potential energy is the energy of position. We know that it is mass times gravity times height, which in this case would be 160,500. So now that we have potential energy, we know that if I had no friction, I would go 100. We would have 160,500 joules of energy transferred from potential energy to kinetic energy at the bottom, right? We know that that would happen, right? But we have this 60 newtons of friction. And if we think about what friction is, it's 60 newtons of friction uniformly dispersed across 500 meters. Each meter, you're getting 60 newtons of friction, negative, which means that I'm actually getting work being done to slow things down. Work is force times distance. So 60, or displacement, 60 times 500, that's the displacement, is equal to 30,000. Did I do that right? Did I calculate the wrong numbers? Maybe I did. Maybe it's the wrong amount. So I said 220, 500 minus 60 times 500, which is 30,000. 190,000. Yeah, I think I did it wrong. And then now that I know that this is 190,000, it's not 160. Let's go back again. 90 times 9.8 times 250. I'm just checking my numbers. Yeah, okay. Minus 30,000. 190,500, not 160. 190,500. 190,500 divided by 45 is equal to 4233, and then I get the square root of that, and that equals to 65. Sorry, 65.06. So slightly higher. 65.06. But the way I knew that I was going to subtract this as joules to joules, is because work is in joules, and so is potential energy. So we have work to energy translation. Once I have work and energy, I don't need to do all that fancy force equals to ma, because look, I'd have like a acceleration of 4.9 and a deceleration of negative 0.667. Then I would have to find out what the velocity is down here. Too much work to do, where I can just use potential energy and kinetic energy and work. There we go. So that's 65.06 is what the actual number is. I made a mistake. All right, guys, that's all I want to cover for today. Way more than I wanted to. I went through that example with you. Take a look at this. A small car with a mass of 1,000 kilograms traveling at 30 meters has its speed reduced to 10 meters per second by a constant braking force over a distance of 75 meters. There's your work, right? Find the car's initial kinetic energy. Find the car's final kinetic energy. The net work done or change in kinetic energy, and find the braking force acting on the car. Guys, each of these questions you see here, there's going to be a variant of them on your test. Guys, thank you so much. I'm going to stop recording now, and I'll take some questions before we stop for the day. So let's go to it.